Take a look at this crowded New York City block. In a fraction of a second, your brain processes the overlap of the vehicles, identifies the pedestrians in the crosswalk, and predicts exactly where they are going to step next. But a computer sees none of that. To a machine, this rich, dynamic environment is a massive grid of raw RGB pixel intensities, entirely composed of numbers arranged in rows and columns. If you feed this image into a traditional neural network, the system requires you to flatten that grid. Every row of pixels is stacked end-to-end into one extremely long, single-file line of data. By forcing a two-dimensional image into a one-dimensional line, the network loses track of which pixels were originally next to each other. The shape of a car door or the curve of a traffic light is erased before the computer even begins to process it. To give a machine the ability to actually see, we have to respect the two-dimensional structure of the data. We need a mathematical operation that scans the image in small, overlapping patches, rather than trying to process a single string of numbers. Machine sight relies on capturing and maintaining the spatial relationships between pixels, rather than simply counting them individually. This local scanning method is called a convolution. The network uses a small numerical matrix called a filter. It slides sequentially across the main grid, performing element-wise multiplication. If the underlying pixels align with the math, say forming a diagonal line, the output spikes, lighting up a neuron to record a match. For decades, human engineers had to write code to create these filters manually. They had to guess the exact math required to detect an edge, a shadow, or a corner. Curious, engaged tone. Modern convolutional neural networks skip that human bottleneck entirely. They ingest millions of data points, calculate precise mathematical patterns, and identify human eyes or wheels. Computer vision efficiency improved as we moved away from human-designed filters, allowing the data itself to define the mathematical requirements for detection. But knowing where the edges are isn't enough to recognize a complex scene. A single layer of detection only gives the network a scattering of lines. To build comprehension, the network must zoom out. It does this through an operation called max pooling. By scanning the data and keeping only the highest values, the network shrinks the dimensions of the grid. This condenses the information, so the next layer of filters can analyze a much wider receptive field. By stacking these steps, the network builds hierarchical abstraction. The first layer finds basic lines. The second layer pools them into geometric shapes. The third layer synthesizes those shapes into complete structures, like the profile of a human face. Through repeated convolutions and pooling, the network bridges the gap between raw data and usable concepts. It organizes thousands of microscopic pixel gradients into high-level, recognizable structures. Everything we just covered makes up the first half of a convolutional neural network. It is a feature extraction factory that can be plugged into vastly different end goals. In a basic classification task, the model uses extracted features to predict a single label for the entire image. The output here is simply taxi. Object detection demands much more. The network must label the object, but also predict its exact coordinates, drawing a bounding box to isolate it from the background. Take a look at this scene. Semantic segmentation pushes the network even further. Instead of an overarching label, the network must classify every single pixel independently, drawing precise boundaries between the animal, the tree, and the sky. Inside this autonomous vehicle, the network isn't classifying categories at all. Combining live visual data with digital maps, it utilizes continuous regression to output a numerical value dictating the exact angle of the steering wheel. Processing data spatially through local patches is an elegant mathematical concept. That single principle scales to solve nearly every complex visual task we give machines today. By evaluating images geometrically, these networks assist medical professionals identifying micropatterns in digital mammograms and provide the spatial awareness required for advanced robotics. Follow our channels to master the architecture behind artificial intelligence. Use the link tree below to connect on Xiaohongshu, WeChat, YouTube, and Spotify. Subscribe, share this with anyone building in AI, and keep learning.